Hello friends. So in continuation with previous video, this is of engineering services examination 2000 on basic soil properties. So the problem is like this. A sample of sand above water table is found to have a natural moisture content of 15%. This is the natural moisture content and a unit weight of 18.84 kilonewton per cubic meter. Lab tests on a dried sample indicated values of zero point 0.5 and 0.85 for minimum and maximum void ratio. So Emax and Eminimum are given. We need to calculate degree of saturation, then relative density, and assume G equal to 2.65. So let's see the solution of this problem. If you look to the solution of this problem, a sample above the water table, a sample of sand. So you have a sample. This sample of sand above the water table was found to have a natural moisture content. So you are given the natural moisture content as 0.15, and a unit weight is also known to you. So the sample has got total unit weight or moist unit weight is given to you as 18.84 kilonewton per cubic meter. So therefore, you need to calculate degree of saturation, relative density, etc. What else are given? If you carry out the lab test on a dried sample, indicated E minimum and E maximum, void ratio minimum and void ratio maximum 0.5 and 0.85. So to calculate the degree of saturation, SR, we have the relationship here that E into void ratio into SR equal to natural moisture content into specific gravity G of the soil solids. Now, the void ratio E can be found out because you know the total unit weight. So total unit weight divided by 1 plus Wn will give you dry unit weight. So therefore, if you calculate this one, gamma D will be 18.84. Let's calculate it. Divided by 1.15. So if we calculate 18.84 divided by 1.15 equal to 16.382. So gamma D is coming out to be 16.382 kilonewton per cubic meter. And we know that gamma D equal to G gamma W. G is given. We know that gamma D equal to G gamma W upon 1 plus E. So on substitution, this will be 2.65 into 9.81 divided by 1 plus E. Therefore, we can simplify and get the value of E equal to 2.65 into 9.81 divided by gamma D, that is 16.382 minus 1. So let's calculate this. 2.65 into 9.81 divided by, this gives you 0.586. So the value of E we have been able to calculate, E equal to 0.586. So void ratio we can easily calculate. Once void ratio is known to you, so on substitution in 1, E is known to you. So degree of saturation, so from 1, degree of saturation SR equal to Wn into G, that is 0.15 into 2.65 divided by 0.586. So if you simplify, the degree of saturation will come. So let's calculate this. 0.15 into 2.65 divided by, so it is coming out to be 0.6773. 0.6773. That is SR equal to 67.73%. In percent, the value of SR will be there. So this is the answer of first part. So this is the answer 1. So it's quite simple to calculate the degree of saturation. Now, you need to calculate the relative density. So, to calculate the relative density dr, we know the formula. So, we can easily calculate it. Now, void ratio is known to us. Degree of saturation is known to us. So let us calculate the relative density. So dr equal to maximum void ratio minus void ratio at the site divided by maximum void ratio minus minimum void ratio into 100, so that you get the relative density in percentage. So here Emax is already given to us. The value of Emax is 0.85. So 0.85 minus the value of E is 0.586 divided by 0.85, and the minimum value is given to us as 0.5 multiplied by 100. So the relative density, therefore, if you calculate, can be obtained very easily. So let's calculate this. 0.5 minus 0.586 divided by 0.35. So we are getting the value as 75.42. 75.42%. So this is the value of relative density. In cohesionless soil, the relative density, because it is sandy soil, so this is the answer of the second part. So this is the answer of part 2, and the value is 75% or more than 70%. Uh, therefore the ground from where you have collected the sample is going to be a dense ground. So it is a dense ground. So relative density gives you an idea about the uh, ground condition, whether it is a poor ground or medium dense or dense ground. Depending upon the relative density, you can easily find it out. So this problem was asked in engineering services examination in 2000. Let's see the next problem now. So our next problem, we will be next problem was of 2011. An oven dry soil sample of volume 225 cc or cubic centimeter weighs 390 grams. If the specific gravity of the soil solids equal to 2.72, determine number 1 void ratio, and shrinkage limit. What will be the water content? Water content which will fully increase, which will fully saturate the sample and cause an increase in volume. Increase in volume equal to 8% of the original volume. So sample is oven dried, and the volume is given to you, weight is given to you. So you have a soil sample. Let's see the solution. We have a soil sample, and the total volume is known to us. And also the oven dry sample, that means there is no water. In three-phase diagram, it will be soil solids. This is the volume of the soil solids from here up to here. This becomes the volume of the soil solids. And the weight is, total weight is given to you as 390 grams. So total weight is also known to you. And GS is already given. So void ratio can be easily found out. If you want to find out the void ratio, because it is oven dried, it is a dry sample. So unit weight, dry unit weight can be computed very easily. If you want to find out gamma D, so weight of dry soil mass per unit volume. So this is going to be 390 gram divided by 225 centimeter. So if you calculate this, you can 1.733. So in gram per cc, it will give you 1.733 gram per cc. Now, once you know the value of gamma D, then you can find out the void ratio. So therefore, void ratio E equal to, E can be calculated very simple, because we know gamma D equal to G gamma W. So it will be G gamma W upon gamma D minus 1, because gamma D equal to the relationship, we know it, G gamma W upon 1 plus. So therefore, E will be equal to G gamma W upon gamma D minus 1. So this void ratio, first part of this problem, therefore E equal to, G is already given to us, that 2.72 multiplied by 1 gram per cc, unit weight of water, divided by 1.733 dry unit weight minus 1. So if you calculate this, you can easily get the value. So 2.72 7.2 divided by this is going to be 0.5692. This is the void ratio. So the answer of the first part is here, E equal to this much. Now, the part 2 is shrinkage limit. So how to find out the shrinkage limit? At shrinkage limit, your sample, the sample will be just saturated. You know the moisture content versus the total volume of the soil mass. It is going to change like this. And here the volume remains constant. This is called the shrinkage limit. Then somewhere here it is going to be the plastic limit. It is going to be liquid limit like this. So the volume remains constant from shrinkage limit, and the sample here is completely filled with water. It is fully saturated. So it is just saturated, and therefore degree of saturation SR will be 100%, that is 1. Hence, the relationship void ratio into degree of saturation SR must be equal to the shrinkage moisture content corresponding to shrinkage limit Ws into the specific gravity of soil solids. This is the relationship. So on substitution over here, we can find it out that E into degree of saturation at shrinkage limit will be 1. So the shrinkage limit Ws multiplied by G value is 2.72. Hence, we can calculate very easily the value of Ws. Therefore, the shrinkage limit will be equal to void ratio, which you have already calculated. So 0.5692 divided by 2.72. So the shrinkage limit divided by 2.72, this gives you in percentage. If you multiply it, this is going to be 0.2092. That means in percentage, the shrinkage limit therefore is going to be shrinkage limit in percentage will be 20.92%. So this is the answer of the second part. Then if you Go to the next part of this problem. What will be the water content? So you will have to find out the water content which will fully saturate the sample and cause an increase in volume equal to 8% of the original volume. So let us see this part, solution of this part now. So we know now the void ratio. E is known to us, and the value of E is 0.5692, and the shrinkage limit is 20.92 percentage. So now let us go to this part. What will be the water content which will fully saturate the sample and cause an increase in the volume equal to 8% of the original volume? The increase in volume will be equal to increase in volume of void. It is fully saturated, and the increase in volume is the increase in volume of void. Let the increase in volume of the void is delta VB, which is given to you as 8% of the original volume. So it is going to be 8% of original volume, which is given in the problem here as 225 cc. So delta V is going to be 0.08 into 225 cc. So if you calculate this one, so this will be 0.08 multiplied by 225 equal to 18. This is the value. Now, the void ratio E is the volume of void upon volume of soil solids. You take any sample here. So, this is the volume of void. Any increase in volume for fully saturated is the increase in the volume of the void. So this is delta V. It is fully saturated. Right? So this is the value, and this is the volume of soil. This becomes the total volume. Right? So E equal to volume of void upon volume of solid, soil solids. And now E is already calculated as 0.5692 equal to volume of void divided by volume of solid. Therefore, you can say that the total volume is the volume of void plus volume of solid. So V divided by Vs, or volume of void divided by volume of solid plus 1. Right? So V by Vs is the void ratio, which is already known to you, equal to 0. Plus 1. So if you add it, this becomes 1.5692. Therefore, the volume of soil solids, this part, can be calculated. The volume of the soil solids, therefore, will be equal to volume of total volume divided by 1.5692. So therefore Vs equal to 225 divided by 1.5692, 143.385 cc. So total volume is known to you as 225, and the volume of soil solids is also known to you as 143.38. So the difference of the two, minus 225, equal to 81.61 cc. So that is the volume of void. Now the volume of void is known to us Therefore, increase in volume, the final volume, therefore, the increase in volume equal to increase in the volume of the void will be simply increase in volume. Cause the increase in volume equal to volume of void plus delta times increase in volume of void. So increase in volume is can be calculated, that is 81.61 plus the increase in volume is by this quantity, and the total volume of void becomes this plus 18. So you can simply calculate this one. So what is the increase in volume can be also calculated. This problem can also be solved in a different way from three-phase diagram also. So let's say if you want to calculate it another way, this is also feasible. So we can also use the solution. We can take another method and solve it. So it's a dry sample. So in three-phase diagram, we can show that the sample is completely dry. So this is the dry sample. And the total volume is given to us, and the total weight is also given to us. Now the weight of air, this part will be 0. The weight of air is going to be 0. So this is the weight of soil solids. This is the weight of soil solids. Now, here in this problem, you have been given the total volume and the weight, and therefore you have been able to calculate the void ratio from gamma d. So the weight of the dry sample divided by the total volume will give you gamma d. This is equal to 390 divided by 225. And this we had calculated that 390 divided by 225, 1.733 gram per cc. And therefore, knowing this gamma d, we had been able to calculate the void ratio. So gamma d was G gamma W upon 1 plus E. Therefore, E equal to G is given to us 2.72 into 1 divided by 1.733 minus 1, and this has given to us 2.72 divided by this minus 1.5692. So this we have already calculated, and shrinkage limit, if you want to calculate this shrinkage limit, so how will you calculate this shrinkage limit? This shrinkage limit, as you have seen, that is the weight of water. At shrinkage limit, the sample is fully saturated or just saturated. So it is the weight of water present in just saturated soil mass upon weight of soil solids. Weight of soil solids is 390 grams. So there is equal to weight of soil solids. And what is the weight of water? So weight of volume of the volume of water, this you should be able to find it out. So then for just saturated, the this can be also calculated by the second method. So because you are given over here the specific gravity of the soil solids, Gs equal to gamma S upon gamma W. So therefore, gamma S equal to G gamma W. And what is this gamma S? Gamma S is the unit weight of soil solids. So weight of soil solids divided by volume of soil solids equal to 2.72 into 1. Therefore, the volume of soil solids will be weight of soil solids, that is 390, and therefore volume of soil solids will be weight of soil solids which is 390, because weight of air is 0, divided by 2.72. So if you calculate it, 390 divided by 2.72 is 143.38 cc. So the volume of the soil solids is equal to 143.38 cc. This is the volume of this. Therefore, we are in a position to calculate now volume of soil solids, and total volume is there. Therefore, volume of void will be equal to 225 total volume minus volume of soil solids, that is 143.38. So let us calculate this. This gives you 81.61. So this volume of void equal to 81.61 cc. Now at shrinkage limit, this will be completely just filled with water, So degree of saturation becomes 1. And WS therefore can be now substituted as weight of water. Now what is the weight of water? It is equal to volume of water. So volume of water into unit weight of water is the weight of water, and weight of soil solids is already known to us as 390. Now volume of water you have just calculated as 81.617 multiplied by 1 divided by 390. So this is how you can also make use of the three-phase diagram and calculate by second method the shrinkage limit. So shrinkage limit, if you simplify it, you will be landing with the same answer. There will not be any change. So 81.617 divided by 390. So 81.617 divided by 390. So this gives you 0.2092. That means it is 20.92%. So either method, whether you are going by first method or by second method, the shrinkage limit answer is going to be same. Void ratio also same, shrinkage limit also same, but I am making use of this three-phase diagram. So you see, the last part was what will be the water content which will fully saturate the sample and cause an increase in the volume of the soil equal to 8%. So the initial volume of the void is already calculated. VVI is already calculated, which was 81.7 cc. Also, we know the volume of the soil solids. This also we have calculated. Now, there is an increase in the volume equal to 8%. So the volume of the void is going to increase by delta V. So delta V we have calculated as 18 cc. Therefore, what is the final void? So final void VVF should be calculated. So the final void is going to be VVI initial void plus what is the increase in the volume which we have calculated. So it becomes 81.7 plus 18. That means it becomes 99.7 cc. So this is 99.7. Therefore, we can find out the void ratio, the final void ratio, because there is increase in volume now. So what is the final void ratio? So volume of void divided by volume of solid. Volume of solid remains unchanged, which is 143.3. So no change in the volume of solid, but this has changed. This is going to be 99.7 divided by 143.3. So the void ratio final can be computed. So this is 0.695. So now, if you use EF into degree of saturation, it is fully saturated. So it becomes 1 equal to the water content, which will fully saturate the sample and cause the increase in volume. So that water's content, let's say it is W1. So W1 into G, and G is already given in the problem as 2.72. So we can calculate it. So therefore, W1 can be calculated as 0.695 divided by 2.72. So this is going to be divided. This is going to be 0.2557. That is, it is 25.57%. So this part, the moisture content is going to be this one. This is the answer. So with this problem is over. Thank you.